Hello everyone and welcome to my thesis defense on the topic Modeling Human Driving from Demonstrations. Here is the autonomous vehicle design cycle, starting with the sensors that transform the scene into something more meaningful. The vehicle has to then make tactical decisions. This involves planning trajectories which the vehicle can take to be able to avoid obstacles and to be able to do meaningful things like staying in lane. Once the trajectory has been planned, that is executed on low-level control, which could involve GPU, power, memory, and compute platform. Then, to actually check whether the vehicle will safely maneuver in the real world, we need environment and human models. So these could be models of how the environment changes based on the vehicle actions and how the other human drivers respond to the vehicle's actions. And these are finally fed into a simulation verification and testing block, which certifies the validity of the algorithm that drives the vehicle. So this is where the importance of modeling human driving comes in these last two blocks, and that is what my thesis is focusing on. I would like to establish my research questions with the help of this video shown on the left. In this video, we see vehicles from Highway 101, and this data is provided by the ngSim dataset. The vehicles in green are recorded trajectories from which we've selected one of them as shown in white here to model. And our model of that vehicle is shown in blue. Now the questions become, firstly, how do we actually model human driving? So how do we model the white vehicle? Second, how do we evaluate how well we have modeled human driving? So how do we see whether the blue vehicle actually is modeling the white vehicle well? And third, how do we actually use the driver models that we have learned? Here is my mental map of what constitutes human driving modeling. We are given a trajectory in all these pictures that is shown in blue. So think of this like a trace of positions of the vehicles from the highway demonstrations. Given this trajectory, we can do interesting things with it. First, we can learn a model. So let's say we have some parametric model parameterized by theta, and the learning is dependent on how close our imitation, as shown in the orange in the picture on the left, is to the blue demonstration. Once we've learned this model, we can do two interesting things using it. Firstly, we can do conditioning, meaning that given the trajectory and the learned model, we can observe the demonstration for a while and then predict what might happen next. We can also do sampling, which means that given the demonstration and using this learned model, we can sample completely novel scenarios. And this is very exciting for the perspective of testing and validation of vehicles, because this allows it to generate traffic simulation platforms to test out autonomous driving algorithms. With that background, I would now like to outline the rest of my talk by laying out the contributions I've made in my thesis. First, to find a black box driver model directly from demonstrations, I'll present an imitation learning based approach. Second, to find an interpretable driver model from demonstrations, I'll present a hybrid rule-based and data-driven approach. And finally, to simulate real-world driving behavior, I'll present a method to do scenario generation and a method to assess the realism using a driving Turing test. Let's jump into the first contribution. So we want to find a black box driver model from demonstrations, and in the rest of this part of the talk, I will tell you how we can go from a recorded demonstrations on the left here through an imitation learning pipeline in the center to a driver model as shown in the right. Here we view driving as a sequential decision-making problem under uncertainty. The pictures on the left represent this. So we have an agent, think of this as our blue vehicle, which takes an action at time t, a sub t. So this could be an acceleration command. And the world, in this case, which means the roadway, responds with a new state s sub t and a new reward rt. So here the new state could be how the vehicle has moved forward and how the other vehicles have moved forward in time. And the reward could be a positive value for the vehicle being able to safely navigate one step further, or a negative value for the vehicle having collided or driven off the road. The picture below shows a Bayesian network representation of the same idea, where we see that the state s sub t evolves to state s sub t plus 1 using the action a sub t. The state and action combine to give a reward r sub t, and the state may not be completely observable and may have to be inferred by some other variable, in this case the observation o sub t. In the driving problem, we have the input, which is the state space and action space. In this case, the state space would be what possible scenes can the vehicle see. For example, what possible locations of the surrounding vehicles and what possible speeds there might be. The action space is what possible commands the vehicle could give, for example, acceleration and turn rate. The transitional model is governed by the vehicle dynamics, so how the vehicle moves forward in time based on the acceleration or turn rate commands given. However, now comes the problem. In Markov decision processes like these, to be able to solve them, meaning to get to a policy which basically maps a state to an action, we need a cost function. In the driving case, specifically for human driving, we don't know what the cost function is. If I asked any of you, when you drive, what is the function you're trying to optimize? I'm pretty sure you won't be able to exactly articulate that function in the state action terms. What we do have though is a set of demonstrated trajectories from the teacher. In this case, that's the recordings we've obtained from ngSim Highway 101 data. So when situations like these is when imitation learning is useful, where the teacher cannot really articulate the cost function or even directly provide a policy, but can provide some demonstrations. And here the desired output we have is that a policy that performs close to the demonstrator. Here is the basic idea behind imitation learning. There is some notation involved which I will explain to you as I go forward. Our goal here is that under some true cost function C true, we want our policy, which is pi here. So think of this as the controller that gives the driving commands to our blue vehicle. We want our policy pi to incur less than or equal to expected cumulative trajectory cost as compared to the expert whose policy is pi e as shown here. But as you may have already spotted, there is a problem here. We don't know what the true cost function C true is. So basically we brute force this requirement. We say, let's assume there is a cost function class mathcal C, and we want to impose this requirement on every possible cost function that belongs to that class. So this means that we want expectation of the cost under our policy pi to be less than equal to expectation of the cost for pi e for all possible cost functions C. However, this is very computational intensive because we have to search over every possible cost function in the class, and we can simplify this by working with the worst possible cost function. So how do we find that? That worst possible cost function C worst is given as a maximum over all the possible cost functions in this mathcal C class of the difference between the expected cost incurred by our learning agent and that incurred by the expert. So once we find this worst possible cost function C worst, the policy finding becomes our standard Markov decision process approach, which is over the space of possible policies, capital pi, we try to find the policy for our learning agent pi, which is minimizing the expected cumulative cost function under this worst possible cost. So combining the worst case cost function finding with the policy finding, we find that the objective function now becomes a minimax problem as shown in the second equation here. So to solve this objective function, we need two ingredients. Firstly, we need a cost function class mathcal C, and secondly, we need an optimization algorithm to find the policy. So traditional apprenticeship learning algorithms would do this by restricting the cost function class to be a linear combination of basis cost functions that the designer would need to specify, and secondly would try and find the policy using dynamic programming based approaches. However, there are problems with this approach. Firstly, what if the true cost function, for example in the driving problem, does not lie in the cost function class mathcal C? And secondly, to be able to learn parametric policies that can work for large, even continuous state action spaces, we need to be able to use approaches that are not just dynamic programming based, but maybe policy gradient approaches. So generative adversarial imitation learning provides these two requirements. Firstly, it removes the assumption of restrictive cost function classes that need to be specified by the designer of the learning agent. And second, it does allow the use of policy gradient approaches to be able to learn parametric policies that can work with large, even continuous state action spaces. So it gives a very simple API that can map relatively low-level features directly to driving actions in our case through deep neural network based driving policies. And the core idea of GAIL here is shown in this picture, where we have the generator, which is the policy which generates state action tuples, and we also have demonstrations from the expert sample. Both these things are fed to a critic, which is basically a binary classifier that tries to distinguish the real samples from the fake or synthetic samples generated by our policy. And the critic then outputs a binary classification decision, yes or no, which is then fed back to the policy gradient approach to iteratively improve the policy further. So how do we use generative adversarial imitation learning, GAIL, in the case of our driver modeling problem? Firstly, we represent the policy, which in this case will be the controller that drives our vehicle, using an RNN, so a recurrent neural network, because we are trying to work with sequential data. The RNN output is used to create a Gaussian distribution over actions, the reasoning being that human actions are always stochastic. So instead of having a deterministic acceleration or turn rate output, we want a distribution over them. The critic, which tries to classify between real and synthetic state action tuples, is represented by a feed-forward multilinear perceptron. And both the policy and the critic get trained simultaneously, so they both play this minimax game against each other and both improve simultaneously. In the table on the right, I'm presenting the features that are provided to the recurrent neural network policy, which inputs these features and accordingly outputs an acceleration and a turn rate command. So these features are for the ego vehicle. It's got its own position, velocity, and placement in the lane. It also looks at vehicles around it, specifically the leading vehicle in terms of relative distance and velocity. And also it throws out some LiDAR-like range and range rate information using artificial LiDAR beams. Further, we have some more features that capture whether the vehicle is driving desirably, meaning if it's within the road or if it's collided or not. On the left, I'm showing a video of the resulting driving behavior obtained using policies trained with GAIL. Here we see that we have selected the white vehicle 2 model, and the model is shown in blue, and it seems to be doing reasonably well. There is close imitation to the demonstrator vehicle, and the blue vehicle also is reasonably staying on the road and not colliding with other vehicles as well. However, when we try and use this learned policy in the case of multiple agent scenarios, because remember, the goal is for us to try and make traffic simulation platforms to assess the safety of autonomous driving algorithms, here's what happens. So we see that the vehicles start off all right, but very soon things seem to go bad. The vehicles start colliding, they go off the road, and everything seems to completely deteriorate. So what this tells us is that imitating multiple vehicles is hard. And this makes sense because GAIL, as it was proposed originally, was proposed for a single agent learning environment. However, our requirement here is to be able to learn driving policies for multiple agents simultaneously. And how do we do that is what comes next. To be able to extend the GAIL approach to multiple agent settings, we have to make a few assumptions. Firstly, we assume that the agents are homogeneous, meaning they all have the same action and observation spaces. Second, we assume that the agents are cooperative. While this is not completely realistic, people may have different objectives and goals as they are driving. This is reasonable to assume because everyone is trying to fundamentally avoid collisions. If this were a racing situation, that wouldn't have been the case because agents are there adversarial. Further, the cooperative agents assumption allows us to use the approach of parameter sharing, which I'll describe subsequently. And the third assumption we make is identical cost function. This is the most unrealistic because every agent, when they are driving, may have different cost functions. For example, someone might be passive, someone else might be aggressive, but this assumption has been done to make the problem tractable. So using these assumptions, what we can now do is we can modify the critic slightly. The critic still remains the same multilayer perceptron, but what changes is the input to the critic. While earlier the state action tuples were provided by experience gathered using only one agent, now we batch together the experience gathered by multiple agents, all being driven by the copies of the same policy, and that experience is then used to improve the policy iteratively. We make one more modification to GAIL to be able to work with our driving problem. As originally proposed, GAIL has no specific information about the domain of the learning agent. In this case, however, we know that the agent is specifically trying to learn how to drive, so we provide something called reward augmentation, where we have external penalty functions to penalize undesirable behavior by the learning agent. So using these two modifications to GAIL, firstly parameter sharing for multi-agent work and reward augmentation to provide domain knowledge, on the left is what the entire pipeline looks like. So first we select some vehicles and we initialize a policy parameterized by theta. All these vehicles now have a copy of this policy using which we roll out. So basically we drive all the vehicles forward a few time steps. That generates the tuples of state actions. And these tuples are then sent to a critic, which also absorbs expert demonstration data. The critic works like a binary classifier, which tries to classify between the expert data and the synthetic state action tuples, and outputs a classification decision. To that output, we also add our external reward augmentation, which is domain knowledge, which penalizes undesirable states. This reward signal is then sent to parameter sharing trust region policy optimization, which is basically a multi-agent extension of the trust region policy optimization approach. And this is used to update the policy, and that process then repeats. So just to repeat, two modifications: parameter sharing for multi-agent work and reward augmentation to provide domain knowledge. Here are some results that compare vanilla GAIL with parameter sharing GAIL and reward augmented parameter sharing GAIL. The pictures on the left are providing us imitation performance. So here on the x-axis we have the time, on the y-axis we have the root mean square error in speed and in lane offset. The root mean square error RMSE compares the ground truth with our rollouts and says how close the rollouts are to the ground truth demonstrations. Here we see that the reward augmented parameter sharing approach gives us the lowest RMSE, meaning it most faithfully imitates the demonstration data. The picture on the top right shows a scaling study, where on the x-axis we have the number of agents, on the y we have the RMSE position. We see that in orange we have the single agent GAIL, and in blue we have the parameter sharing GAIL, and we see that as the number of agents increases, the deterioration in performance of the single agent is much worse as compared to the parameter sharing approach. So while both the pictures on the left and the top right provide imitation performance, we also want to see how the overall traffic looks, and that's provided by the picture on the bottom right, where I am showing you a distribution of the speed over all the vehicles over all the time steps in the rollouts. Here in the black we see the demonstration speed distribution. The orange shows the speed distribution obtained by GAIL, and the green shows the distribution obtained by reward augmented parameter sharing GAIL. And we find that the distribution is very close to the demonstration in the case of Rails, showing that it's giving you much better overall emergent traffic flow as compared to vanilla GAIL. The video on the left shows the resulting driving behavior obtained using GAIL with the parameter sharing and reward augmentation modifications. Unlike in the previous case, we now see that the driving is pretty reasonable, with all the vehicles staying on the road and no collisions being shown at all. It's fascinating to see that without even knowing what driving mean, what lanes mean, or what even roads mean, the deep neural network policy has been able to successfully drive reasonably well in a multi-agent setting. However, this is a very cherry-picked video, and things are not always this good, as shown by the picture on the right, where I am presenting to you the undesirable incidents in the rollout trajectories obtained using our driving policies. Here we have off-the-road duration, collision rate, and hard braking, all of which are 0 for the demonstration data ngsim as shown in the black, but none of them are 0 for our GAIL-based policies. And the biggest issue is that if you ask me why do the vehicles still collide, I don't have a good answer for that, because given that these are deep driving policies, there is no interpretability. So to summarize this section, I presented generative adversarial imitation learning as a viable approach to modeling human driving behavior. And I presented two methodologies to change GAIL for the multi-agent modeling and driving problem specifically. For the multi-agent modeling, I presented parameter sharing that used the assumption of cooperation between agents. And to provide domain knowledge, I presented the reward augmentation approach, where we provided the learning agent with external rewards to specify its driving behavior. However, there are certain limitations to this approach. Firstly, The GAIL-based methods cannot generate reliable traffic simulations all the time because the vehicles still collide and they still drive off the road sometimes. Second, the method lacks interpretability. So whenever we see collisions or other undesirable driving incidents, we can't explain the reasoning because all the driving policies are basically deep neural network based policies. And finally, the method does not capture individual driving behavior and is extremely data hungry. The lack of interpretability in deep reinforcement learning and imitation learning based methods motivated the second contribution of this thesis, which is to find an interpretable driver model from demonstrations. I'll present a hybrid rule-based and data-driven approach. There is a line of existing work on rule-based driver modeling that rely on interpretable parameters. The most important thing here is that safety is baked into the driver models, so the vehicles are guaranteed to be collision-free. However, these models have traditionally relied on heuristics to set the parameter values and are thus very brittle and don't generalize well to novel scenarios. In this part of the talk, I will present an approach where we learn the parameters of rule-based models from driving demonstration data. And this allows us to also capture individual driving behavior as opposed to aggregate that was the case in the imitation learning based approach. The underlying rule-based model we'll use for this part of the work is the intelligent driver model, which is a guaranteed collision-free lane-following driver model that relies on parameters that govern the driving behavior. The two equations on the right describe the intelligent driver model. Firstly, the desired spacing between the ego vehicle and the leader vehicle is calculated using parameters like the minimum separation, the minimum time gap, and the limits on the acceleration values. This desired spacing is then used to compute an acceleration output called as AIDM here, which is a fourth order nonlinear equation in terms of the ego vehicle's velocity and the relative speed and spacing between the ego and the leader vehicle. But let me remind you that the goal here is to model human driving, which is stochastic. So we make a modification to the IDM and call it the stochastic IDM. Here, the actual acceleration is sampled from a Gaussian around the predicted IDM acceleration output. And the new position is then sampled according to a dynamics update using the stochastic IDM. The equations on the right describe this whole process. So we use the IDM acceleration output, A sub IDM, and we add one more parameter, which is the standard deviation of the Gaussian around this A sub IDM, and we call it sigma sub IDM. The actual acceleration is then sampled from this Gaussian. The position is updated according to xt plus 1 equals xt plus half a delta t squared, where delta t is the time step, and that results in the true position being distributed according to the Gaussian centered at the calculated position with a standard deviation of sigma sub IDM times delta t squared. Now, having created the stochastic IDM model, we cast the driver modeling problem as Bayesian inference. The picture on the left describes this. Suppose we have a position trace xt and xt plus 1, which is governed by hidden parameters of the model as shown by the vector theta here. So now the observations are vehicle positions from driving demonstration data, and we have to solve the equation given below the picture, where you want to find the distribution over the parameters theta given a sequence of positions x1 to t. And you will recognize this as the Bayesian inference problem, which can be solved using recursive Bayesian estimation. To solve this estimation problem, in this case, we use particle filtering. The reason being that the underlying model is a nonlinear model, which does not admit techniques like Kalman filtering or extended Kalman filtering. I will now describe the particle filtering approach using some pictures. So let's say we have only two parameters for the sake of illustration. The actual underlying rule-based model, the stochastic IDM, will have 5 parameters. So here, suppose theta1, theta2 are the two parameters, and our belief over the parameter values is represented by this box of particles. And we are trying to here infer the parameters of this green vehicle from demonstration data. And the red vehicles are the surrounding vehicles that we are not trying to infer parameters for. So let's say we select one particle from this bucket of particles and use that as the parameter setting to hallucinate the vehicle forward one step in time, as shown by the picture in the middle. So let's say that the vehicle now hallucinates forward as given by the blue circle with the mean given by the blue dot. So let me remind you that the reason there is a circle here is because the next position is sampled according to a bivariate Gaussian. And now we weight the respective particle according to the likelihood of the ground truth as shown in the green dot in the last picture on the right under the Gaussian distribution given by the blue circle. So we now similarly repeat the process for all the particles in our parameter belief. And we end up with a set of weighted particles as shown in the picture on the middle. And we add some dithering noise to perturb them. This is standard in particle filtering. And as shown in the picture on the right, we then resample from this new set of particles and move the vehicle forward one step in time and repeat the whole procedure. So this is how the demonstration data is used progressively to refine our parameter space to something that is closer to the true parameter setting as represented by the particles converging to closer regions of that true parameter. Now to assess the performance of our particle filtering based models, we use some baselines to compare against. Firstly, we use constant velocity and constant acceleration models that basically drive the vehicles with constant values and also do not react to the other vehicles. The second baseline we use is the intelligent driver model with parameters as recommended in the literature, which are basically set using heuristics. The third baseline is a black box model, which is our generative adversarial imitation learning based model. The fourth baseline is the parameter values fit for IDM using nonlinear least squares, so which is using the Levenberg-Marquardt method. The picture on the right shows an example of the kind of results we may expect. Here again, I'm showing for illustrative purposes only a two-dimensional parameter space with the desired velocity on the x-axis and the stochasticity, so sigma sub IDM, on the y-axis. And there are 20 vehicles here represented on this two-dimensional parameter space. And as we can see, every vehicle has their individual parameter value, which reinforces what I said earlier, which is that this method allows us to capture individual driving behavior as opposed to aggregating everything together. To assess the performance of our particle filtering based method, we do experiments where we, in addition to the previous ngSim highway driving dataset, I've also used another dataset from Germany, which is shown in the picture on the top left. This is called the Heidi dataset, which is recorded using a drone on German highways. The animation on the top right shows the progress of particle filtering as data is shown to it. Here again, I'm presenting a desired velocity versus stochasticity two-dimensional parameter space. And we see that as the particles, as the demonstration data is shown, the particles converge with more data. The picture on the bottom left shows an example of the ngSim and Heidi datasets, where the blue is the ngSim and the red is the Heidi. And every point here represents a different vehicle with its resulting parameter values. And we can see that as we expect, the German vehicles have higher values of desired velocity. And this shows that we're able to recover the fact that German highways have no speed limits, which allows the vehicle to drive faster. Here are some results from the experiments we conducted. The picture on the left shows the number of undesirable instances. Our model, which is IDM sub theta, is shown in the red here. And as we expect, all the intelligent driver model based approaches, including ours, show no collisions at all. This is great because as we started off with, the safety is baked into the driver models, so the vehicles are collision free. On the other hand, approaches like the constant acceleration and constant velocity do show collisions because the vehicles don't react to the other agents around them. And the GAIL based approach, as shown in the blue here, also shows collisions, as we have seen in part 1 of this talk as well. The picture on the right shows the imitation performance, where again I'm presenting the root mean square error between the rollouts and the ground truth demonstrations. Here we see that the IDM sub theta, which is our particle filtering based method, shows the lowest value of RMSE, proving that it is the most faithful to the demonstration data. Here is the resulting driving behavior obtained using our particle filtering based model. The animation on the right shows pairwise parameters from the 8-dimensional parameter space, which drives the underlying lane following and lane changing model. Here again, we see that as more and more demonstration data is shown, the particles do converge and result in one point estimate of the parameters. This video shows us an example in this lane overtaking situation. As always, we have the white representing ground truth demonstration, and the blue shows us the model that we have learned. And there seems to be good agreement between the white and the blue, showing that we are able to faithfully represent the demonstration data in this lane overtaking situation. I'd like to conclude this section by giving a summary and its limitations. So here I presented an approach which uses rule-based models that are inherently safe but generally brittle due to heuristics. So I presented an approach that does online parameter learning for parameters of rule-based models from demonstration data. I used the technique of particle filtering, which is very simple and well established, to do this parameter estimation problem. However, there are some limitations to this approach as well. Firstly, this method needs a model and is only as good as that model. So for situations where there are no underlying rule-based models available, the approach will not work. Second, we assume that the parameters do not change over time, which is again not very realistic because drivers do change their behavior over time based on the situation. So far, we've seen a method to do direct black box driver modeling from demonstrations using imitation learning, and a method to do hybrid rule-based and data-driven modeling for interpretable driver models. My third contribution in my thesis is a method to simulate real-world driving behavior and assess the realism using a driving Turing test. For this part of the talk, we will now focus on merging scenarios, while so far we've looked at highway driving on straight highways. Merging is a challenging real-world situation that involves negotiation between various driving agents. And scenario generation is important to be able to build traffic simulators to assess the safety of autonomous driving algorithms in simulation. The underlying rule-based model we use for this section is the cooperative intelligent driver model. This picture on the right will help us explain the model. Suppose the green vehicle is being driven by the cooperative IDM, which depends on another parameter called C, in addition to the existing parameters of the intelligent driver model. So if C is equal to 1, then the green vehicle is a cooperative driver and allows the blue vehicle in front to merge in front of it. And if C equal to 0, then the green vehicle is completely uncooperative and does not allow the blue vehicle to merge in front and just drives on straight as if it's driven by vanilla IDM. As in the previous contribution, for this section as well, we baseline our particle filtering based method against vanilla intelligent driver model, a nonlinear least squares based intelligent driver model, and CIDM, which is the cooperative IDM with maximum possible cooperation level. The picture on the right shows the imitation performance with time step on the x-axis and root mean square error on the y-axis. And we see that our particle filtering based method gives us the lowest RMSE, meaning the most faithful modeling of the driving demonstration behavior. On the right, to capture the emergent driving behavior, I am presenting the speed distribution as a probability density function. Here, the brown curve shows the underlying ground truth speed distribution, and we find that the particle filtering based method has the closest speed distribution to the demonstrated method. Here are some videos to illustrate the driver models. This video shows the ground truth demonstrations in a merging situation involving 4 vehicles. Here is how the intelligent driver model based models will drive in this situation. So here we basically start the vehicles at the same location as they were in the ground truth, but then drive them forward using the vanilla intelligent driver model. And as we know, the IDM does not understand merging, so we see the vehicles 250 and 249 colliding at this merge point. Here is how the vehicles will drive when they are driven by CIDM, so the maximum possible cooperation level. And we see that the vehicle 250 and 256 come to a complete standstill. So even though they are not colliding and hence are very safe, they're not very efficient. This last video shows the particle filtering based method in action. So here we see that the cooperative IDM has its parameters learned using our particle filtering method. and we find that it's closest to the ground truth demonstration in comparison to the vanilla IDM and the cooperative IDM with max cooperation. To assess the realism of the driving behavior obtained using our particle filtering based method to infer the parameters of the cooperative intelligent driver model, we performed a driving Turing test. Here, we generated synthetic videos, 10 of them, and showed them to 21 human respondents. The picture on the left shows the misclassification performed by the human respondents. On the x-axis, we have the different ID of the various human responders, and on the y-axis, we have the different scenarios, so there are 10 of them. The picture on the right shows the corresponding confusion matrix, where we see that there are a significant number of false negatives and false positives. The accuracy obtained here is 55%, which makes us very happy because it says that we are able to fool human participants into thinking that synthetic videos created using our driver models are classified by them as being real driving demonstrations. I'd like to conclude this section by providing a discussion and providing the associated limitations of the method. Here we looked at merging, which is a challenging driving task that involves negotiation with other agents. We used the stochastic cooperative IDM as the underlying rule-based models and learned the parameters of this rule-based model using particle filtering from the interaction dataset, which contains merging demonstrations. We then used a driving Turing test to assess the realism of the driver models learned using our method, where we showed synthetic and real videos to human participants and asked them to classify them as being real versus fake. There are a few limitations to this method. Firstly, we didn't model the impact of ego vehicles on the surrounding agents. So this means that whenever an ego vehicle takes an action, the surround vehicles also react, but we have not modeled that interactive behavior. Second, most of the Turing test participants here were autonomous driving researchers, which may have biased the Turing test results a bit. Here is a summary of the 3 contributions I talked about in this talk. First, to find a black box driver model from demonstrations, I presented generative adversarial imitation learning and 2 modifications. Firstly, parameter sharing to enable modeling multiple agents, and reward augmentation to provide domain knowledge. Second, to find an interpretable driver model from demonstrations, I presented a hybrid rule-based and data-driven approach using particle filtering, where I learned the distribution over the parameter of the stochastic intelligent driver model from 2 real-world driving datasets, ngSim and HiD. Third, to simulate real-world driving behavior, I presented a scenario generation method and a driving Turing test. Here, the parameters of a learned distribution were sampled from the stochastic cooperative IDM to drive in a merging situation, and the experiments were performed from merging data from a real-world dataset called the interaction dataset. There are interesting directions for future work. On the left, I am presenting some possible avenues of future work from relaxing the assumptions. Firstly, this thesis assumed cooperative agents, which allowed us to use the method of parameter sharing in the imitation learning approach. However, in real-world driving, the agents are not always cooperative, and neither are they completely adversarial. So we need a way to model the spectrum from complete cooperation to complete adversarial behavior. Second, I assumed complete observability in this thesis, which is that there was no need to model the internal traits or intents of the drivers. In future work, I plan to investigate how modeling the internal intents and traits impacts the prediction performance of our driver modeling methods. In this work, I also assumed that the parameters were not varying with time, meaning that the drivers did not change their driving style, which is again a very restrictive assumption. So future work can investigate how to model time varying parameters in the driving demonstration data. Finally, we assume that the interaction was not to be modeled between the vehicles. So in the situation like merging, where interaction between agents is crucial, we did not model that. So future work will try and use some methods from game theoretic analysis to model the impact of ego agents on the other agents around and their reaction to it as well. Some broader research directions emerging from this work are, firstly, we need to learn hierarchical models. So here, I directly mapped driving scenes to low-level driving actions like acceleration and turn rate. However, when we actually drive, there is a high-level planner like a Google map which says turn right in 200 meters. And that turn right intent governs our low-level driving actions. Second, the models that I've learned from this work can now be used in two ways. Firstly, these models can help planning. So suppose an autonomous vehicle has a planner like Monte Carlo tree search, so that the hallucination of that planner can use our learned models to propagate the state forward in time. Second, the learned models in this thesis can be used for risk analysis to find most likely failure scenarios in safety certification of autonomous driving algorithms. Finally, the methods here were demonstrated on modeling human driving, but they can very easily transition to other human motion modeling tasks. For example, modeling human behavior around indoor and warehouse robots, pedestrian modeling, and crowd modeling for disaster response situations. Thank you very much.